Okay, so what is a limit? So a limit is used to describe how a function behaves as its input, which is what we call the independent variable x, approaches some value y. So how does the function behave as x approaches some other value? Okay, even if the output doesn't exist. And I phrased this weirdly. I stole this from somebody else, and now that I read this out loud, I don't like the way that it's phrased. I'm gonna edit some of the stuff in here, so scribble with me. We want to know how the function behaves. I want to know how this output behaves, not this output, as x approaches, and I'm going to use the number a lot. So let's put an a right there instead of a y. So really, I want to know how y, the output, behaves when x gets close to some number, which I'm going to just call a. That's how I should have written that. Okay, and in this section, we're going to look at just limits of functions that have a single input, not multiple inputs. That's later calculus 3, multivariable calculus. But when we talk about functions of one variable, there are only 3 forms to the limit. Okay, there is the limit, so write LIM to be short for limit. Underneath the limit, write x, and then draw an arrow to a. And above and to the right in the superscript, write a minus sign. Actually, write a plus sign. We'll start with the plus sign. And then put f of x next to it. So it kind of looks like in trig, when you have sine of something or cosine of something, I'm using a word here, or at least an abbreviation of it to describe what we're doing. This is what I'm going to call a right-hand limit. And that will become clearer in just a second. The second form of the limit looks almost exactly the same. X, draw an arrow, write the letter A, and then in its exponent area, write a minus sign. And I'll describe what this means in just a second, but we're going to call that a left-hand limit. And then the final form will have no plus or minus. So the limit as x goes to a of just f of x. Okay, and that's just called the limit. So we got a right-hand limit, a left-hand limit, and just, maybe I'll write it, the limit. Now the difference between these is, again, we're going to study what happens to the function as we approach a. So draw a horizontal number line. Imagine this is like the x-axis, and here's where the value a is. The right-hand limit is the limit as we come in from the right. Okay, this as x approaches a plus means come in from the plus side of a, meaning come in from above a, to the right of a, from larger than a, get closer and closer to a. So if a was 5, I would start with like maybe 10, and then 6, and then 5.5, and then 5.1, and 5.01. Those are numbers that are getting closer to 5, but they're from the right-hand side, right, coming in this way. On the other hand, if I come in from this direction, I'm going to say that's x approaching a from the minus side, which makes sense if you think in terms of, you know, where positive numbers and negative numbers are on the x-axis, okay? In a minute, we'll look at a graph and we'll see what we're actually looking at as we get closer is what happens to the height of the graph as we come in from that direction, okay? And then the limit, this general limit over here, is going to mean that if the limit from the left of f of x is a number and the limit from the right is that same number, then that's what the limit is equal to. As long as the limit from the left and the limit from the right are the same number, they come into the same height, then that's what we're going to say the limit of the function is at that point. Excuse me. Coffee. Okay. So here's the idea. For this notation, the a plus means come in from the plus side. A minus means come into A from the left side, right? And then if when you come in, you get to the same height on both sides, that's what you mean when the limit equals that value. A lot of practice coming up, so you'll get the hang of this as you see some pictures. But let's write one more thing, because this is terminology that is commonly used in this context. We say that the limit of f of x as x approaches A is equal to L. When we say that, and maybe I should even write that out. When you see this written, you need to know how to read that. When we say, I have to take this off. I'm sorry. Can't write. It's just going to make it worse, but I'm going to, just for class today. The limit as x approaches A of f of x is L. So when we say that, what do we mean? We mean that the value of f of x can get as close to L, this number here, the thing that it's equal to, that is the output of f of x gets really close to L, as close as we like, by taking x sufficiently close to A, but not necessarily equal to. So when we say the limit as x approaches A of f of x is L, what we mean is that the value of f of x can be made as close to L as we like by taking x sufficiently close to A. First way I want to teach you is graphically. If you have a picture, it's fairly easy from a graphic picture, a graphical representation of a function, to figure out what the limits are. Okay? So I've grouped these kind of together. Let's look at this first one. Notice in all three of these, I am approaching the value -1. So the question is, if I approach x goes to -1 from the, and what direction does minus mean? What direction am I coming in from? Left. If I approach from the left, what is happening to the function if this is f? So I first go to -1 on the x-axis, because that's what I'm approaching, and I come in from the left. What is the height of my function getting close to?
5.
As I come in this way, notice I get closer and closer to 5. So that's exactly right. The answer is 5. Does everybody see where Boston got 5? What if I come in from the right? It's also 5. Okay? And the point of all these examples is it's not always the same, but in this case, it's pretty clearly the same. If I come in from this side and I come in from this side, I'm coming to the same height, right? So if they're both the same and I don't have a minus or a plus, that just means what's the limit? And the only time this has a value is if the limit from the left and the limit from the right are exactly the same. If they're the same, then that's the answer, so this is 5. We would say the limit at x equals -1 is 5, which means the height of this graph can get as close to 5 as we want by taking x to be sufficiently close to -1. Just using the language that we filled in the blanks at the bottom of the previous page. All right, let's jump over to 1, which is right here, and you'll see there's some different behavior going on. I've got 4 questions now. What's the limit as we come in from the left as x approaches 1? It's 5. Notice it doesn't matter what happens at 1, it's only what do we get close to as we come in. And what's the limit then as we come in from the right? It's way down here. So do you see how up here I'm getting close to a height of 5? Down here, if I come in from this direction to 1, I'm getting close to a height of -2. So if those aren't equal to each other, then this limit right here doesn't have a value. It's only equal to the value whenever they're the same. So what we will say in these circumstances is the limit does not exist. Or I can write it as a backwards E with a line through it. That's my preferred notation. But both of those mean does not exist. And the reason I write this in here is some textbooks use that. Our online homework uses that. So you can't type this in, obviously, into the online homework because that key is not on your keyboard. But you can type D and E. So whenever you have a problem on the homework where it's not a value and it doesn't exist, D and E. Now, what is the actual function value at 1? What's the output to x equals 1? And how did you come up with that? That dot, right? So open circle means that's not the value. Open circle means that's not the value. So we indicate that that is the output by writing 3. So notice this function can have a different limit from the left, from the right, and a value at the function can be all different. That's fabulous, okay? So that's one of the things that we sometimes just assume later on is that the limit of some function exists and is equal to the value at the point, but we can have ugly functions, and this is kind of an ugly function. Okay. All right. What about 5? From the left, it is 2. From the right, coming into 5, 5's right here. From the left, it's 2. From the right, it's 2. So what's the limit? 2. If those are the same, then that's the value of the limit. What's the value of the function at 2? D and E, because there's no dot. So you can actually have functions whose limit exists, but the function itself does not have a value. Okay? And we'll come back to all of those concepts in the next, or 2 sections down the road, when we define our favorite kinds of functions, which are called continuous functions. The continuous functions are the ones where, like this first block up here, the limit exists. It's the same from both the left, the right, and even the function value at that point are all the same thing. Those are nice functions, but they're not the only kind of functions that are out there. All right, about what we got -3 from the left and -3 from the right. So in this case, notice something weird is going on where we've got these arrows, right? You guys probably have a vocabulary for that. What does that look like is happening? It's asymptotically approaching. It's an asymptote. It's getting close to it, right? The closer you get to -3 from the left and the right, the closer it appears to be getting that line. And my arrows are just indicating that it's going to keep on going forever, right? So how would you write the fact that if I come in from, say, the left, what is the height of that graph getting close to? It's negative because it's going down, and it's infinity because it goes on forever. Okay, and the notation you guys are probably most familiar with infinity is the sideways 8, right? It's a specific type of infinity. The longer you're in math classes, you will eventually learn that there are actually different kinds of infinity, different sizes of infinity. All this means is to keep going forever. Okay, grow without bound. Okay, so this gets further and further negative and has no upper limit. It just keeps on going forever. You see how we got infinity because it goes on forever, and it's negative because it's under the curve going down, right? And if I were to come in from the left, sorry, from the right, as I come in this direction, right, and then I'm on this curve that's coming down here, it's going down this way. It's also going to negative infinity. And since they're the same, then the answer is negative infinity. That's how we would write that. Now, if you go back to 4, where the other vertical asymptote appears to be, this other thing that we're approaching, what happens when we come in from the left? positive infinity because it's going up. So I would just write infinity. And when I come in from the right, negative infinity. So what would you say is the limit as x goes to 4? They're almost, I mean, they're very similar. They're both growing without bound, but one's going up, one's going down. So you're right. We would say, because they're not exactly the same, does not exist. And the last two questions here, actually, before I fill those in, let me just point out these two right here. When you have something where the output of the limit goes to infinity, that is that terminology that you just introduced in here. It's called asymptotes, and they're vertical. So x equals a is said to be a vertical asymptote, asymptote, of the function. If any one of these statements is true, that the limit as x goes to a from the left is infinity, x goes to a from the right is infinity, x goes to a from the left is negative infinity, or x goes to, I'm just going to put commas in here, so to emphasize the fact that it's any one of them can be true. And it's called a vertical asymptote. So I gave you an example where from both sides they were going to the same infinity or two different infinities. You can even have the case where, say, here's a, you've got a vertical line here, say the function does this, but then on the right hand side it starts right away. It doesn't go to infinity or anything. Okay, you can have it going to infinity only on one side but not the other, and that is still a vertical asymptote. So that's what I mean when I say any one of them can be true. Just only needs at least one. So above, in this example right here, what are the vertical asymptotes? Specifically, what's the equation of those asymptotes? And I wrote it this way on purpose, right? That's the equation of a vertical line. So the actual lines are x equals -3 and x equals 4, exactly. So you had it. We're just going to write it like that to indicate that that vertical line is the asymptote. Cool? We good so far? Once you get to graphs, it's actually pretty easy to tell. You just got to be able to train yourself to think moving along the curve from that direction, Okay? The last one is, what happens if I move the infinity to the thing that we're approaching? This terminology can be formalized, and we probably won't get to it until actually much later, but this is the idea of let x go all the way down the number line in the positive direction and let x go all the way down the number line in the negative direction. So instead of getting close to something, actually we're doing the opposite and getting as far away from everything as possible. Just keep going. Okay, so if I was going to go to your right, that would be the limit as x goes to infinity, positive infinity. So if I look at this picture, what happens as I travel out all the way? What does it look like is happening to this graph? Well, it's going up here, right? This is x goes to infinity. It's going to go up, we assume, forever, right? So the answer to that would be infinity, because it goes up forever. And what's the limit as x goes to negative infinity? It's negative infinity, not because this is negative infinity, but when you look at the picture, you see it going down, right? As x goes to negative infinity, I'm going downhill as I go further out. Yes?
Plus or minus. Like no restrictions trying to come from.
Okay, so in positive infinity, when there's nothing in front of it, means to go in the positive direction. So we don't put a symbol up here. There's only one way to get bigger and bigger positive, and that's from the left, because there's no right of positive. Let me do this way. There's no right of positive infinity, right? Because you keep going forever. No matter where you stop and try to come the other way, you're eventually going to go past it. So you don't have a plus or a minus in the superscript because you can't come to positive infinity from the right. And you can't come from negative infinity from the left. So we're going to always go to the right for positive infinity and to the left from the right side, but going all the way out that direction. Does that make sense? All right, let's go to the next one. One of the problems I gave you in your homework looks very similar to this. It's a problem where I gave you what's called a piecewise function. I'm sure you've seen a piecewise defined function before, but even if you haven't, it's not that hard to understand. A piecewise function means there are different pieces to it, and instead of me just drawing the pieces for you, I gave you the equations of each of the pieces, and then I'm going to ask you a question about that graph. So if I asked you to graph this, you actually got 3 graphing problems in one, and you got to make sure you understand what is meant by the restriction on each line. So this says that the output of a function, f of x, is 4 plus x whenever the input is less than -1. It's x squared when the value is between -1 and +1 and including -1. And 2 minus x if x is greater than or equal to 1. So here's what I would do to graph this before I answer the question. First thing I'm going to do is I'm going to draw my axes, and I've got this right here so I can cheat on my screen. You have to draw as accurate as you can by hand. But here's my graph, and I'm going to do, this is -1, this is +1, so that's my scale. And let's just think intelligently about what we know. So the first piece of the graph you have there is that when x is less than -1, so that's to the left of -1, the graph of the function over here is it 4 plus x or x plus 4? It's 4 plus x. So first of all, what do you know is the shape of a graph of a function that looks like that? It's a diagonal line, right? We know it has a slope of 1 because that's the number in front of the x. That's some of your algebra skills right there. This is like y equals mx plus b. I just got the order switched. So we know it's a slope of 1, and I can actually figure out what's the height of that line at -1. I just plug in one of my endpoints. It's 3, right? So I need to go 1, 2, 3. So that line would have a height up here of 3. And I'm going to put a circle right there because this piece says strictly less than -1. So it doesn't actually have that value at -1. If I gave an x to a -1, I would have to plug it into the second piece. Right? F of -1, I would use this piece right here because that's when x is -1. But the line over here to the left-hand side is a diagonal slope of 1. That means if I go to the right, it goes over 1, up 1. If I go to the left, it would be left 1, down 1. So I know if I plug in, say, -2, I'm right here. If I plug in -3, I'm right here. So this line just looks like this. That's what the piece to the left of -1 looks like. Between -1 and +1 is x squared. What does x squared look like? Parabola. At -1, it has a value of 1 because -1 squared is 1. And I'm going to put a solid dot at -1, height 1, okay, because of the equal to that's included in this inequality. And then a circle right here at +1, and I'm going to draw the parabola. Standard parabola that we know that x squared looks like. And then to the right, 2 minus x, so that is another line, and it has a slope of -1, which means for every 1 I go over, I go down 1. Right? Rise over run. So if my rise is negative, then I'm going to have to go down 1 for every 1 that I go over. So it's going to go down 1, over 1. It's this line right here. And since it's or equal to, I can plug in 1 into this equation, and it also has a height of 1, so there's actually a dot right there. And it goes down 1 over 1 like this. This is the graph of that piecewise function, okay? Because in here it's x squared, and over here it's 2 minus x. And I put dots corresponding to where the output would be based on the or equal signs in my inequality. Okay, so that's the graph. if you look at this graph and then I ask the question, what values for A would the limit not exist? That is, are there places on this graph where if I come in from the left and I come in from the right, I come into two different heights? Right? Because for the limit to exist, they have to come into the same value. Notice, for example, this value right here is actually okay. Because if I come in from the left to 1 and I come in from the right to 1, my height is going to 1 from both sides. Okay? What's the only value of A? That is, if I wrote limit as x goes to a of f of x, where the answer would be D and E. You see -1 being the problem? It's the only place it's broken, right? So broken lines are places where the limit does not exist. So I would say A equals -1 is the only one. Cool. Okay, moving forward. Another thing that you can do, and this gives you more confidence than it should, so don't trust this method as much as you trust the graphing method, and definitely don't trust either of these methods as well as you trust the actual analytical techniques we're going to learn in 2.3. But another way that you can find a limit, especially if the graph isn't nice and neat, is to use a table of values. Like, I mean, just imagine a situation where instead of, I'm going to back up for a second, instead of maybe the limit as x goes to -1, what if I ask you, what's the limit on this graph as x goes to -5? It's right here, right? Which is not quite 5. It's certainly not 4. It's somewhere in between. So you're guessing, right? And you know, in some cases that may be the problem I ask. I might say estimate what it is, but I want to know exactly what it is, right? It's very possible that even formulas that I give you, not just graphs, but formulas, don't go to nice, neat whole numbers. Okay, we get spoiled by homework problems where the answer is always 1 or 0 or -5, right on the number, right? We will often see things ugly and nasty in here. So in those cases, another kind of brute force technique is to just use some values and get closer and closer to that. By closer and closer, what I'm saying is, let's say I want to take the limit as x goes to 0. So on a real number line, if 0 is here, I want to take some values and get closer from both sides. So maybe from the right, I could plug in a 1. And then I could maybe plug in a 0.5. And then I could plug in a 0.1. Okay, and so on. I could get closer and closer and closer and plug those values in and see what happens. So that's a second way to evaluate a limit. Okay, again, it's sloppy, it's brute force, not to be derogatory or anything, but that's an engineering approach. Okay, we just use our calculators. It's not the mathematical approach, it's the let's just guess and check kind of thing. Again, not bad, but not the best. But for this homework, this is what I'm going to ask you to do. So you could, with your calculator, go in and take 1 and plug it into this formula and evaluate it. Okay, which is what I would recommend that you do. It gets a little bit annoying when you have 10 values to plug in and you want to get their outputs and you have to type all of that into your calculator. I'm going to let you decide how you want to do this. I'm going to show you real quickly what I would do because I have tools at my fingertips on the web that allow me to create a formula that I can plug things into. So don't necessarily have to learn how to do this from me right now, but you could go back and watch this video and figure out how to do this yourself. I'm going to use what's called a computer algebra system, which lets me create formulas that I can plug into. One of my favorites, you've seen me use Desmos before, but I'm going to use GeoGebra. I think I tried to use GeoGebra a little bit one time in here. It didn't go as well. I'm going to use the calculator. I just go to geogebra.org and I start my calculator. And it's got some graphing stuff, but I'm really just going to use this pane over here, and I'm going to type f of x equals, try that again, f of x equals, And then I'm going to type in either using this palette down here at the bottom or just typing the keys in the formula for the function that I want, this guy up here. So I'm going to do the square root of x squared plus 16. Go outside there and do minus 4. And then I'm going to highlight all of that and turn it into a fraction. Actually, I'll tell you what, I'm just going to highlight it, put parentheses around it, divide it by, and I think it was x squared. So now, I don't care what the graph looks like. What I care about is what happens when I plug in 1. So that graph looks, that function formula looks exactly like what I have in my notes. So I can now plug in f of 1. If I were to stick in 1 here and do 1 squared plus 16, it gives me 17. Square root of 17 minus 4 divided by 1 squared, that gives me this number 0.1231056. That's the output that I get. So I'm going to write that down in my table, which since I have not enough screen space, I'll drag it over here and I can write it off to the side. And this is 0.1231056. I'll do 7 decimal places. If I repeat that same thing again, this is why I like using a computer algebra system. I can just now write f of 0.5. And I get another number. It just calculates it for me. That one is 1245155. So 0.1245155. And I'll go ahead and tell you what I get if I do f of 0.1. You see what I'm doing? I mean, I'm choosing numbers closer and closer to 1 from the right-hand side and seeing what happens to the output. This gives me 0.1249804. If I plug in 0.05, it's 1249951. And the next one is 0.1249998. So over here, this seems to tell me that the limit as x goes to 0 from the right of f of x is about what? What does it look like these are getting close to? 125, which is 1/8, by the way. But that's not enough to tell you the limit. That's only the right-hand limit. So if I come in from the left-hand side, what do I get? So if I plugged in -1 into this formula, without even doing it, can you tell what it has to be? It's got to be that, right? Why? If you look at the squares, right, it's going to just strip off the negative anyways. So you're going to get the same answer, 0.1231056, 0.1245155, 0.1249804. I'm just writing down the same thing to the left over here on the right. 0.1249951 and 0.1249998. It appears that this is going to the same thing, 125 from the left, which would mean you put these two pieces together and you get your answer. I would say the answer is that's 5. Sorry, 125, 0.125. I don't know why I said 5. That's the answer. Sorry, they get sloppy and fast at the end. I'm running short on time, so I wanted you to see that. So that's how I might use a calculator or a table of values to figure out these limits as well. Okay, so for these last examples, these last 3, I have it under a section of using your mathematical intuition. You can think through what you would expect to happen, but that also does not rule out the possibility that you can just go graph these. You can go to GeoGebra or Desmos and graph them, or you can use the table of values, right? So In the rest of the examples in this section, I just want you to think about what you think would happen. And if you can't tell by looking, go and do a graph to it. So let's do, here in the last 4 minutes, let's at least tackle this one, which is this sine of pi over x. So before we tackle this, let's have a quick refresher of just what sine means. Okay, you've had trig, or at least pre-cal, before you've gotten here before. Yes? I sure hope so, because you're going to be lost if you've never seen a sine function before. Some of you will have learned SOHCAHTOA very, very well. SOHCAHTOA is to define trig functions in terms of right triangles. If this is your angle theta, right? If you draw a triangle like this, if this is, say, we call this the opposite side from the theta, this is the adjacent side to the theta, this is called the hypotenuse. We know that sine is
Y over.
yeah, y. If you call this y, you call this x, you call this r. It's y over r, or opposite over adjacent. That's where the SOH comes from, right? So just a quick point here. If the theta is 0, what does this definition tell you sine of theta is? If the angle is flat, sine would be 0, right? Because the opposite would be 0. The height of it would be 0, right? And the adjacent would still have some, not adjacent. Why did I write adjacent? You guys have been staring at me squinting. What should I have written right there? Thank you. I don't know what I was. Anyway, hypotenuse. You were all there. I wasn't. Opposite over hypotenuse. Yes, that makes more sense now. I didn't run off and leave you and start making up my own mathematics again. It's flat. The hypotenuse is still non-zero whenever it's, say, 0 angle. Still has a length, but the height would be 0. The opposite would be 0. Cosine is adjacent over hypotenuse, and then tangent is opposite over adjacent. That's the thing I wrote before. But many of you, especially the ones that took it from me last semester, will remember the unit circle definition, right? Which now you do your theta on a unit circle, and the definition of sine of theta in that case is the y coordinate. If you think of that as x comma y, right? And then your cosine is the x coordinate, and your tangent is the ratio of those two, so it's y over x. Okay, so both of these pieces help you recall what some of the common trig function values are for sine and cosine and tangent. You know that if you plug in, say, one of the angles that end up on an axis, like, say, 90 degrees or pi over 4, sorry, pi over 2, pi over 4 is 45 degrees. But say you're talking about, like, this angle right here. You know, sine of 90 degrees is going to be the y coordinate of that point. That's where you get 1, right? Because the height is 1 because you're on the unit circle. Makes it easy to find those. But this is also a good way, if you remember your 45, 45, 90 triangles and your 30, 60, 90 triangles, your reference triangles. All things that, you know, you'll want to refresh on and we'll come across here. But for now, let's just think about what's happening to this function as x goes to 0. So before we think about the sine, what's happening inside? X is on bottom, and the bottom of a fraction is going close to 0. So it's getting smaller and smaller and smaller, close to 0. What happens to a fraction if its denominator gets smaller? It gets bigger, right? So the whole fraction inside here is getting bigger and bigger and bigger. Now what happens to the sine function as things get bigger? you got to go back and remember what the graph of sine looks like. You remember what the graph of sine does? It's a wave, right? Starts at 0 and just goes back and forth. Okay, that's a horrible sine wave, but that's the thing. So as this thing in here gets bigger and bigger, right, all sine's going to do is bounce back and forth. So this is the graph of sine, not of sine of pi over x. If I were to actually graph this, what is happening is as I come in towards 0, it's like taking what's happening going out to the right and squeezing it in as I come in from the right. Okay, the graph ends up looking something like this. It bounces back and forth, back and forth. The closer I get, it bounces back and forth. So from this graph, which you could get, by the way, by plugging into a graphing tool, but you can also reason out with your mathematical intuition, what does it appear is happening to the limit as x goes to 0? Is it getting close to anything? Well, the x is getting close to 0, but what about the height?
Stays the same. It changes every.
It doesn't go, yeah, it's changing. So what are you thinking it stays the same as? It's kind of like what the sine is doing, but it never goes above +1, never goes below -1. So it stays in that range, but it's still bouncing back and forth. In fact, the closer you get to 0, the faster it bounces. So is it getting close to a single height? The answer is no. So we would say it does not exist. Okay, now I'm out of time. Let me just at least write the answer down. You could figure this out by graphing, by table, or by intuition. What happens as you come in from the right to 4? Okay, this one, since x is bigger than 4 when you're coming in from the right, the bottom of this fraction is positive. Does that make sense what I just said? Right, if you come in from the right from 4, that's like 5, 4.5, 4.1, 4.01, and if you were to plug that into this x, you would have a positive number. But the bottom of this fraction is going to get closer and closer to 0 when x gets close to 4, which means the bottom of a fraction gets close to 0, the fraction gets bigger. When the bottom gets smaller, the whole fraction gets bigger, and it's getting bigger to positive infinity. This one is also going to be positive infinity. You can get there by seeing that the bottom of this thing is always positive, and as it gets close to 0, the bottom of the fraction is getting smaller and smaller and smaller, but the whole fraction then is getting bigger. It's blowing up. Okay, and just for funsies, you could go plug these into Desmos or GeoGebra and see what the graph actually looks like. I'll do one of them, not both of them, and then that's where we'll stop. If I were to plug in here, f of x equals 1 divided by x minus 4, enter, you can see the picture right there. And what happens when you come in from the right to 4, blows up. The theory of relativity and the mass of a particle that has a velocity v, and you've got m naught, m sub 0, you've got a v, which is the velocity of that particle, and you've got c, which is a constant. It's the speed of light. Okay, so the mass of the particle can be calculated by this formula. The question is, what is the limit of this formula as v approaches c? And you've got the little minus sign up there. What does that minus sign mean up here from the left side? Okay, so let's think about the variable v and where it shows up in this equation. Again, I'm trying to find the limit as v goes to c from the left of this whole formula. I'll put the m naught on top, m sub 0 on top, over the square root of 1 minus v squared over c squared. So the place where that v comes into place is right here. So notice what happens to this as v gets close to c. Just the part that I have highlighted. What happens to that as v approaches c? It gets close to 1, right? In fact, if you just plugged in the c for v, you would have c squared over c squared, so it's 1, right? Does that make sense? So as the top gets closer and closer to the bottom, it becomes more and more like c squared over c squared, which means it's going to 1, right? But the minus sign makes a difference. As the v squared is coming up to c squared, right, then this number is slightly less than 1. Right? Since we're coming from the left. If we were coming down from the right, then that number would be slightly more than 1. Right? But for every value where you're coming up from the left to c, then the top is a little bit smaller than the bottom, which makes the highlighted thing slightly less than 1, right? And on bottom, if you take 1 minus something slightly smaller than 1, right? Then is that positive or negative? Positive, right? It's positive. But it's getting smaller and smaller and smaller because 1 minus something smaller than it but close to it is getting closer and closer to 0, right? So now this whole thing right here is getting close to 0, but is positive. Now you don't have to write all this down when you're doing a homework problem or you're doing a test question, but this is my thinking to figure out how I'm going to come up with this answer. And then what happens when you take the square root of something getting close to 0? It also gets close to 0. Right? Square root of 0 is 0. So the whole bottom of the fraction is getting closer and closer to 0. The top is going to stay the same because that's the mass of the particle at rest. So if you take a number that's staying the same and divide it by something that's getting smaller and smaller and smaller, like dividing by 1 and then 0.1 and then 0.01 and 0.001, what happens to the whole fraction when the denominator gets small? It gets bigger. It's bigger and bigger and bigger and never stops getting bigger, right? So this thing is going to go to infinity, but since the bottom is positive, right, then it's going to go to positive infinity. I could not just say what's the limit as v goes to c without the minus sign, because the problem you run into is if your value of v is slightly bigger than c, then the denominator becomes negative, right? And you can't take the square root of a negative. So that's why the minus sign is important in this problem. If we were going the other side, it would just not have any values. But since we're coming in from the left, we know this is getting close to 1, but is slightly smaller than 1. So 1 minus something slightly smaller than 1 is getting close to 0, but it's positive. And when the bottom of a fraction is getting close to 0, the whole thing gets bigger, which means it goes to infinity. Okay, so you see how we thought through that process? One of the things that you've got to learn in this class, and this is going to happen more and more with the mathematics that you take, especially you guys that are engineers or math majors or computer science majors, the more math that you have to take, the less it's like algebra, where in algebra I said, here's the recipe for how to do a problem, just do exactly what I do on your own. Calculus becomes more where every problem is its own thing that you have to think through and use all the skills that we've developed, but it may be a little bit different every single time. Okay, so I'm going to throw in problems like that occasionally. I will stop recording, and then we'll